Okay, let me just mention something that I worked through and rewrote the sections on Minkowski space, Lorentz transformation. In fact, I combined those two sections together because I thought they were somewhat repetitive. And I hope the new version is better. If you want, I could tell you something about the new version, or I could just move on. I need a little guidance from the students.
Move on.
Okay, well anyway, it's periodically I throw the new PDF from chapter 11 or chapter 10 onto the class webpage. Turns out that the IT department at UNM has shut down the campus, shut down the department website, but they don't know about my website yet. So,
Wait, why did they shut down?
It was back
Oh.
an hour ago again, so.
It what?
Lord knows. In fact, they've sworn Tom Hess to secrecy. He can't even tell us what the problem is. The IT department here has enormous power and confidence that exceeds their intelligence by many orders of magnitude. They make the FBI look gentle, sensitive, and polite.
Well, the website is, the UNM website is not up to par, I'm just going to say that.
Okay, anyway, all right, so I'll just tell you guys, go look at the new version if you want to. And as usual, if you see something wrong with it, send me an email or tell me about it in class. Tell me about it in class, you get candy.
What?
Is anybody starving?
She is right here.
Oh yeah, I'll take them. Oh my gosh, yes.
Anybody else hungry? All
No,
right.
you guys need to look like an asshole.
Okay. All right. The first thing.
I have a question about the,
Good catch.
Wow.
question about the projects or homework, whatever you said we're doing. Would we be considered double dipping if we do something that works for two classes?
Whatever makes you happy.
I'm taking the neutrino seminar also.
Candy.
There's a lot
Wait a
of
minute, I've got a vulture coming in here.
Whoa, thank you, Lord. Thanks a lot.
and I was
Back to me.
You're taking which course?
the neutrino seminar with Albury, and there's basically they started a book last semester, and so I'm trying to catch up on that. It's Schutze's relativity book, and so I'm working through a lot of those things. Seems like it's close, but I don't know if I'm gonna have time to do all of that.
Whatever makes you happy.
I'll turn it in, and you can decide what you want.
Sure. Okay. I'm going to talk about today. I'm going to start out talking about something that's mainly notation, but it's a very amusing notation, and it's due to a French mathematician who was born in 1869, the son of a blacksmith, but he managed to get an education and became probably the greatest French mathematician in recent history. His name is Cartan, and Elie is his first name. Of course, when I pronounce something in French, it's meant to be an approximation, not the absolute true form. Now, so the subject is differential forms, and what's one of the nice things about the notation, first of all, notation is very cute, okay, and the French are known for doing things in elegant, cute ways. But on the other hand, by the way, Chomsky has a YouTube video where he criticizes French intellectuals, and I'm surprised he could travel to that country at this point. Anyhow, what's cool about this, you see, is here's a one form, and it's now what's cool about that is you see AI is a covariant vector, dxi are the contravariant infinitesimal differentials. So this is automatically invariant under coordinate transformations, arbitrary coordinate, as long as they're, one-to-one, smooth, so on and so forth. So, and this is called a one form. And as I said, what's cool about it is that it's a notation in which the quantities, these forms, are automatically invariant quantities. And that's something really nice from the point of view of having equations that are true in arbitrary coordinate systems. And the reason why you want that is that nobody guarantees that the coordinate system we might be using is the right coordinate system. Okay, anyway, so let's suppose we change our coordinates. How do these things change? Well, AI is covariant, so it turns into partial xj, partial x prime I, j, and then dxi prime is just a chain rule, so that's partial x prime I, partial xk, say, dxk, and there really is a prime there. And then the ordinary rules of calculus say that the partial of xj with respect to x prime I times the partial of x prime I with respect to xk, and we're implicitly summing over I. So this is, in other words, this thing is summed over I, and these things are, in other words, if I, instead of using the summation convention, if I just put this in, then we're summing over I, j, and k, and if we're talking in ordinary terms about force space that we live in, then it's summed over from 0 to 3. Anyway, this thing gives you then partial xj, partial xk, aj, dxk, but this is just a Kronecker delta. And so this is delta jk, aj, dxk, and that is just aj, well, let's use k, ak, dxk. So in other words, in an arbitrary coordinate system, A prime is the same as A, so the one form is invariant. I just wanted to say that explicitly. And that's the cool thing about forms, namely that they're invariant under coordinate transformations. This notation involves, well, the definition of the one form doesn't involve it, but there is something called a wedge product. This is called a wedge product, wedge being this thing that looks like that. And first of all, the wedge product is automatically anti-symmetric. So if you write dy in front of dx, you get a minus sign. And in particular, that means that dx wedge dx has to be 0, because it's also equal to minus dx wedge dx. And so to 2 dx wedge dx is 0. Now, what's cool about this? Well, dx wedge dy, it's like a cross product in that what you have is that this is the area spanned by dx and dy, and it has a sign, namely that it's the sign, it's whatever sign comes out when you take dx wedge dy. In other words, it's different from dy wedge dx. And now, let me just point out something that's cute about it. Suppose you go from coordinates xy to coordinates uv. And then you look at du wedge dv. Well, du wedge dv, du is partial of u with respect to x times dx plus partial u with respect to y times dy. And then we wedge this with partial v partial x dx plus partial v partial y dy. Okay, now what happens here is the dx wedge dx is 0 and dy wedge dy is 0. And so du wedge dv is then simply partial u partial x times dx dy, but then minus, well, maybe I should do this in 2 steps. Partial u partial x partial v partial y dx wedge dy, and then the other term is plus partial u partial y times partial v partial x, and this is dy wedge dx. But the dy, the wedge product's antisymmetric, and so this is partial u partial x partial v partial y minus partial u partial y partial v partial x dx wedge dy. Okay, this thing here is a determinant of these partial derivatives. In other words, it's partial. Let me use u sub x as, let me call this u sub x and call this v sub y. This is just another notation for partial derivatives. Then this is ux, let me get this right, vy uy dx. It's that determinant times dx wedge dy. And this thing is then the Jacobian of the transformation times dx wedge dy. So what the Jacobians do and what this wedge product does is that it arranges for, in other words, the wedge product automatically builds in the Jacobian, which ensures that if you change variables in an integration over some surface, that you get the right answer. I think what I should do is add to the web page of the course a section. The Jacobians are in chapter 1 of the book, and I'll throw that web page, those web pages onto the thing, onto the class web page. but in your calculus courses, you get Jacobians, right? At some point? Not yet?
It's usually toward the end of Calc 3.
Yeah, we did a little bit.
You got it, all right, well,
But
all right, well, let's hope then that the stuff that I put on the class webpage is good enough. So if you have a cause du wedge dv, that by itself isn't something that's invariant. We want things that are invariant. And so what we do, for example, is we make two forms, and two forms look like this. 1/2 HIK dxi wedge dxk. Okay, now this, if this is a covariant rank 2 tensor, then the wedge product of these two contravariant differentials will be a contravariant tensor summed over I and k. You then get a scalar. And so this is an invariant quantity H. And being invariant, that's something really nice. That that's the nice thing about forms, is that they naturally give you these invariant quantities. So this is called a two form. And mathematicians can't resist. If something works for 1 and 2, then it works for an arbitrary integer, so they call it a p form. But the p form k, normally we put a 1/2 in front of a 2 form, 1 over p factorial, and then it's ki1 ... ip, and then dxi1 wedge ... wedge dx ip. Okay, so that's a p form, but I don't know. I don't think I've ever used anything more than a 2 form. Okay, so we've had a little bit of notation here. First is the definition of a form as an invariant combination of vectors or tensors with wedge products of coordinate differentials. That's one aspect of differential forms. Another aspect is something... break my neck over all this stuff. Another aspect of things which is also cute. So as I said, this notation of forms is cute. And if, well, anyway, let me just show it to you. There's something called the exterior derivative. Not quite sure why the term is used, but anyway, it's always written as d. And what does it do? It differentiates, so it differentiates and adds a differential. So add some sort of differential. So let's just look at the simplest example. Suppose you have a function, f. Well, this is a 0 form. So I imagine that this is itself invariant, so it's a scalar function. df is a 1 form, and it's partial f, partial xi, dxi. So that's a 1 form. And so what d does is it automatically turns a form into a higher form. So for example, suppose we had a 1 form, a equal to aj dxj. Then dA will be partial aj, partial, say, xk, dxk, wedge, dxj. So that's how it works. So it turns a one form into a two form. And it's really cute like that. You don't want to use one of these things to hold your paper? Okay. All right, so it turns a one form into a two form. And in particular, if we're in three space, so that these indices just run from 1 to 3, then one of the famous cases is let A be a sub x dx plus, a sub y dy plus a sub z dz. So in other words, this is a dot dx, which is the way we might write this one form in 3 dimensions. Then dA, I'm going to skip all the intermediate steps, they're in the class notes. But dA, what is that? Well, that is curl of a z component, dx wedge dy, plus curl of a, let me get these straight, y component dz wedge dx, plus curl of a x component dx, wait a minute, that's wrong, dz here. Oh, I did z. This was supposed to be x. Z.
The top one should be y.
Yes. Thank you.
The last would be z.
My goodness, you're going to get so much candy. It's
Oh.
going I could have, of course,
Give
read.
her, she's hungry.
It's a feast. I know. Things are good tonight.
Oh, you need notes on this?
So you're sorry?
Oh, yay. Thank you. Look at that. That's a full dinner right there. I'm kidding. I eat. Right.
Okay. So dA turns curl of a, I'm sorry, dA turns the one form into a two form involving the curl. Now, one of the really famous in physics one forms is the electromagnetic potential or the electromagnetic field. In other words, A0 here is the scalar potential, and the three components of A are the vector potential, and you turn that into a one form, and okay, so that's the one form. Now here's the cool thing: this exterior derivative turns dA into, well, d of aj dxj, and that is di of aj, say. So this means d sub I is partial with respect to x upper I. Maybe I should just write it. But this is anti-symmetric. And so this is 1/2 of the Faraday tensor dxi wedge dxj, where this Fij is partial aj partial xi minus partial ai partial x. J. I should have used I and K. Let me write a note to myself to that effect. I've been trying to avoid using I and J together because they're so easily confused. Okay, now, you might say this can turn into a nightmare if you hit this with another exterior derivative, if you're going to have so many wedge products and so many derivatives, it's all going to be confusing. Well, it turns out that d squared is 0. The square of the exterior derivative is 0. Now, why is it 0? It's 0 in this sense. So suppose d acts first on something that we can call qi, which is dxi wedge ... So in other words, this is some p-fold, let us say. We hit it with the exterior derivative, and then we hit it again with the exterior derivative. We're going to get 0. And the reason for that is that the first one, this one here, is going to be partial qi, partial xk, say, dxk, wedge, dxi, wedge, ... And then when the d hits that, what we're going to have is the second partial qi with respect to, let's call it L. Okay, now the reason this is 0 is that this part is antisymmetric in L and K. And this is obviously symmetric in L and K. And so, for example, what this would be terms like this. Partial 2qi, partial x1, partial x2, dx1 wedge, dx2, and then it would also have a term partial qi, partial x2, partial x1, dx2 wedge, dx1. Well, these two guys are the same, so we could just erase the 2 and the 1 with a 1 here and a 2 there. So now these two are the same as they were before, but these two are opposite, so they cancel. So the whole thing is 0. So the square of the exterior derivative is 0. And so that is neat. That's the general impression one gets, is that it's just very cute. Now, here what we have, of course, is dx wedge dxk is antisymmetric. But on the other hand, if we just wrote the two together, then these guys would be symmetric. In other words, this would be the same as dxk, dxl. So in other words, if you have an arbitrary tensor, M, well, second rank covariant, and you have dxi wedge dxk, then only the antisymmetric part of the tensor contributes or survives. Of course, again, I'm always using the summation convention. So we're summing over I, we're summing over k, however many the values that takes. So only the antisymmetric part contributes. On the other hand, if we have something like this, MIK dxi dxk, this is also invariant, but only the symmetric part of the tensor would contribute. Now, remember I said here that d squared is 0, and then over here, what we said is that dA is what we can call f being 1/2 Fij dxi wedge dxj. But that means that dDA, which is dF, has to be 0. That's 2 of Maxwell's equations. Maxwell has, well, there are 4 equations, there are really 8 equations, because 2 are vector equations, 2 are vector equations, and 3 vector equations, the other 2 are ordinary equations, so there are really 8 equations. 4 of the 8 equations are given by just dDA equals 0, where A is just this one form here. So as you can see, this is a really cute notation. On the other hand, I don't think if you're taking a graduate course in classical electrodynamics, I don't think you can just get away with saying that d squared is 0 and that's the end of it. This thing, by the way, this equation here, EF equals 0, this is called the Bianchi identity. Anyway, it's half the Maxwell equation. It's the homogeneous Maxwell equation. Okay, now a couple of definitions. Suppose H is some form and DH is 0. If then we say H is closed, it looks like dosed the way I wrote it. Okay. So if DH is 0, H is closed. So in particular, F, the Faraday form, is closed because DF is 0. On the other hand, some H is exact if H is dk, where k is some other form. This would be a lower form, because d raises the form level. So, a p form H is exact if it's a differential of a p minus 1 form k.
So does that mean all exact P forms are closed?
Yes. Good for you. You get a candy.
No.
Maybe you get the candy. I don't know. Anyway, so consequently, suppose H is exact, then DH is DDK 0, so H is closed. So all exact forms are closed. Shall shall I just,
I don't really know. I'm sorry, he said you were hungry, so I'm pointing your way.
You're my best friend right now.
okay.
Someone tell me to stop it now.
Okay, now, Poincaré,
You want to
Poincaré's, I don't know, brother or cousin or something was president of France at some point. Okay, what did I want to say here? Poincaré, had many results, and there's a lemma that bears his name, which says that every closed form is locally exact. In other words, let me just explain one. If dH is 0, then locally H is some dk. Locally meaning in some suitably small volume or whatever. There's another thing that's another feature of forms that's kind of amusing, and in fact it's of interest historically, I think. So we've got this one form, A, AI dxi, and now we might say, well, what if we take A wedge A? Well, if we take A wedge A, then we're going to get things like this: AI, AK, DXI, DXK. Okay. But on the other hand, these guys are anti-symmetric. What about these? Well, in the early days, now let me put it this way, since I don't know that much about it. I don't know a lot about the history of mathematics or physics, for that matter. Some people used to, and some probably still, look at this equation and say this is automatically 0. But you see, the AIs could be things that don't commute with each other. For example, they could be group elements or matrices that don't commute with each other. Or, God forbid, they could be Grassmann variables, which, just a joke, which are anti-symmetric, anti-commuting. In other words, the Grassmann variable, theta I, theta j is minus theta j, theta I. So, if these things are Grassmann, or if they're matrices, or if they're operators, in other words, they have derivatives of things, or they're quantum mechanical objects, quantum mechanical operators. In all these cases, what we wind up with is 1/2 the commutator of AI, AK, DXI, wedge, I forgot the wedge here, DXK. Let me see, I've got the factor of 2 right here. Yeah, apparently. Yeah.
For Grassmann numbers or Grassmann variables, is there any other way of representing them other than just... So when I first heard about Grassmann variables, I decided I was really dumb and I was going to figure out if there was a matrix version. And there isn't. I mean...
Well, no, you can represent Grassmann variables by matrices. The trouble is the matrices... Yeah, the trouble is the matrices get big.
Okay.
All right, I tell you what, I've got a couple of pages from chapter 1 on Grassmann variables. I don't know why, probably a marketing mistake to put Grassmann variables on page 3 or 2 of the book. But I did anyway, and I just thought it was good to show students things and then tell them to, all right, there you've seen it, now forget about it for the time being. Anyway, I'll put that stuff on the board.
Obviously, I was wrong. I kept getting all.
What?
I kept getting all of the entries being 0 for everything that I tried to do. So I must have done it wrong.
Well, the trouble is if you have n Grassmann variables, I think the matrices are 2 to the n by 2 to the n. So if you have 2 of them, they're already 4 by 4. And I'm just remembering, it could be n minus 1, it could be n plus 1, I don't remember exactly, actually, I think 2 by 2. Yeah, I think it is 2 by 2 because, for example, if you just have 2 Grassmann variables, you could just use 2 of the Pauli matrices. Right? So in other words, you could say theta 1 is and theta 2. Of course, I've used something that's complex there, but you could have used theta 3. Okay, let me use theta 3 here, so I don't even have to use complex numbers. Okay, so suppose we multiply theta 1 times theta 2. 0, 1, 1, 0, 1, 0, 0, minus 1, and we get 0, 1, minus 1, 0. On the other hand, if we multiply theta 2, theta 1, 1, 0, 0, minus 1, 0, 1, 1, 0, what we get is 0, minus 1, 1, 0. And you see these two things add up to 0. So you can write Grassmann variable, if you have 2, you only have 2 of them, you can write the 2 of them as matrices like that. Actually, now that I think about it, what I just said is wrong. So, and the reason for that is that Grassmann variables are such that theta I squared is always 0. But theta 1 squared isn't 0. So what you need is an extra 1. So in other words, if you have 2 Grassmann variables, I think you need 4 by 4 matrices. All right, I'll add that to the class website. It's okay. So anyway, we weren't really talking. I mean, Grassmann variables are not something that I'm going to talk much about in this course. Yeah, you might want to turn that thing around. Here, I'll do it if you want, then you don't have to get up.
Oh, that's all right. I got it.
Okay, so let's go to the whiteboard now. I pick up a piece of chalk. All right, let me remind you of some electrodynamics, or actually electrostatics. So, if B dot is 0, then the curl of E is 0. That's one of, that's Faraday's law, and Faraday's law, by the way, is part of the Bianchi identity. And so we can make a one form, E, equal to EI dxi. And we can hit that with the exterior derivative, and that's going to give us partial J EI dxj wedge dxi, and this is really the curl. So this is a half partial J EI minus partial I dj dxj wedge dxi. And that's 0 because that's Faraday's law when B dot is 0. And so in particular, if you're in the case of magnetostatics, that is to say the magnetic field is static, then this is the case. And dE is 0, and so we would say E is closed. E is closed. Okay, well, what I said was that Poincaré has a lemma to the effect that if E is closed, then locally it's exact. And let's notice, first of all, that we can take EI of x dxi, and we can integrate from some p to some, on some path from some point x0 up to x. And we can call this a potential associated with this integral. Now the problem with this being a potential is that v depends not only on x, but also on the path. Because if you integrate along a different path, you're going to get, in general, a different result. But because of this Poincaré lemma, you can arrange that at least locally, this thing will be path independent. Because V of P prime minus V of P would be an integral of EI dxi, which would be an integral of the curl of E dot, say, ds over the surface that's bounded by the two curves, P and P prime, from x0 to x. Okay. And so what one can arrange then is that this is the case. And so what we normally do in magnetostatics, electrostatics, is we say that E is minus the gradient of some potential V of x. And so what we're leaning on there is the, well, actually, I've got the logic, I've made this more complicated than necessary. Because, I mean, if we have B dot equals 0, then the curl of E is 0, and then we always have the thing is path independent. If we didn't have this, then what we would say is that we could arrange that locally it was true. But
if curl is everywhere 0, I'm pretty sure there's a theorem that says
what?
If curl is uniformly 0, I'm pretty sure there's a theorem that says that any two paths are between the same points are equivalent.
Oh, well, absolutely, yeah. So if the curl is 0, then the difference of the two is the integral of E up one path and then down the other. And that is the integral of the curl over the surface that is bounded by the two paths. And so if curl of E is 0 there, then the two paths are, the integral along the two paths are the same. Okay. Or, I don't know, it's really you guys who should say okay rather than I, but I somehow got into this habit. I've got to break myself of it. All right, well, this is all related to Stokes' theorem, and the general form of Stokes' theorem is that the integral along the boundary of a region, mathematicians use this partial derivative acting on the region to mean the boundary on the region. I don't know why they do that, but it's a standard notation. So we're integrating a p-form H over the boundary. This is the same thing as the p+1 form over the region. And that's the general form of Stokes' theorem. And it's true for arbitrary p-forms. So it's again one of these really cute, neat things. So what we've seen here, this is the p-form, this is the case p equal to 2, p equal to 1. The case p equal to 2 is a theorem in elementary calculus, namely that h of b, so suppose h is a 0 form, that is to say it's just a function. H of b minus h of a then is an integral, the boundary of R integrating h. Well, what's R? What's R? R is this region from A to B. It's just a region on the real line from A to B. The boundary of R is just essentially B and the 2 points, B and A. And so this is equal to the dH on the region, and this is what we call the integral from A to B of dH of x, which is to say the integral from A to B of the derivative of h dx. And so we have then this formula from calculus, which is that a function h of b minus a function h of a is the integral of the derivative of h from A to B. And so that's a particular case of this form of notation. Now there's one other thing that's worth noting here about these forms, about the exterior derivative acting on forms. And let's just look at it from the case of D acting on two forms, the wedge product of two forms. And suppose they're just one form to make it simple. So this is D on AI dxi wedge bk dxk. So this is going to be partial AI partial xl dxl wedge dxi wedge dxk bk. So I'm assuming here that A and B well, I haven't commuted them, so this is still correct. Next, this D is going to act over here. So, whoops, I didn't want to do that. And in fact, now that I think about it, I should actually follow my notes because it's important to get the signs right here. Well, the trouble is I switched notation, so I'm going to have to do this live. Okay, so now the D is going to hit this, so we're going to have AI dxi, and now the D is going to hit this, and we're going to have partial B, K, partial XL, say, dxl wedge dxk. All right, let me, goodness. Let me give you the, instead of going through this algebra with all this notation, this is dA wedge B, that first term. But now this second term, it turns out to be minus A wedge dB. And let's see. Let me make sure that I've done this correctly here. No, I didn't. Okay, the point here is that the derivative, this exterior derivative, acts with a derivative on B, but the dxl is out to the left. It's still to the left. So this would be dxl, dxi, and so forth. And now, if you want to bring the dxi out next to the ai, it has to cross the dxl, and that's the minus sign. Okay. Anyway, it's clear in the notes. It's just that I wanted to avoid having I and J here, and so I introduced an L, and that meant that I couldn't just follow what was in the notes. Okay, now, sorry about the other thing. Let me go back to this business about tensor equations and about their being useful. And the nice thing is that they're true. If you have a tensor equation, it's true in any coordinates. So for instance, we had this, one of Maxwell's equations or actually four of them look like this, DI F JK plus DKF IJ plus DJF KI. And since all the indices in each monomial here, all the indices are different, there's no sum. And IJK can take four values, 0, 1, 2, or 3. Consequently, suppose IJ and K are all space indices, in that case, we've left out 0, time index. But we could have left out one of the space indices. So altogether, there are really 4 equations here. And this, in fact, is just the Bianchi identity. So this is the same thing as df, which is dA, which is automatically 0. So these are the four homogeneous Maxwell equations. And what you see is that they're tensor equations. The inhomogeneous equations look like this, and this is, we'll get to this in the general relativity part, which is Thursday or next week. Square root of G, Fik, partial xk, mu 0, I'm talking in vacuum, so that's, actually no, this is not vacuum. Square root of G, Ji. So these are the free, that's the free current. G is the metric of space-time that occurs in general relativity. So these are the inhomogeneous, the four inhomogeneous Maxwell equations. We're summing over K for each of the four possible values of I. You have an equation here. Okay. So these are generally covariant tensor equations. And what's nice about equations like this is if you write them like this as tensor equations, and if they're true in one coordinate system, then they're going to be true in any other coordinate system. Because in any other coordinate system, these things would be partial x prime k, partial x I, say, partial x prime L, partial x R, say, G I R. So if this is 0 for all values k and L in one coordinate system, then in another coordinate system there's still 0. So that's the nice thing about tensor equations. That is to say, the physical laws are the same when expressed, same in all coordinate systems when expressed in terms of invariant forms. And so if you write a theory in terms of tensors or forms, you get a theory whose equations are true in all coordinate systems if they're true in any coordinate system. And one way to do that is what I mentioned last time, which is to say you use an action principle with an action that's invariant under coordinate transformation. All right. Let me state now I've been throwing an awful lot of stuff at you in these lectures, so just, ducks can tolerate rain. So students, just tolerate this stuff. If it's too much, just listen to some music or something. But also ask questions.
Your equation there with the square root of G, you said that's...
Which equation are we talking about? This one or that one?
That one.
This one?
Yes. The G, is that...
This is just an ordinary partial derivative with respect to xk.
So, but is the G, is that a component, or is that the entire...
You take the k derivative of the square root of G times Fik, and then sum over k, keeping I fixed.
The G is what I'm asking about. Was that
G.
the determinant of the metric?
Oh, okay, all right, here. And pass it on if you want. G, I'm taking it to be the absolute value of the determinant of Gik. That's my notation.
Okay.
Other people have square root of minus G. Well, I don't want all these minus signs in every equation, so I just have square root of G. All right, there's something called the quotient theorem. And the quotient theorem is a big relief. Suppose you have BA, these are two forms or tensors, and you don't know what this is. You don't know what B is. But you know that this thing is some kind of a tensor for all A's of a given rank or kind. All right, let me give you an example, because the example will make it clear, I hope. So in other words, suppose BI AI is BI prime A prime I for all contravariant vectors A. We don't know what the B's are, but we're saying that for all contravariant vectors, we have this relation. Well, you might suspect that B is a covariant vector, and you'd be right. This is called the quotient theorem. And it's probably worth proving, so let me just show you what this is. Let's say what this is. Well, this is BI prime, and this is partial x prime I, partial x k, a k, and that has to be, let me change this index to a k now, summed over k here. And so what we have then is BI prime partial x prime I partial xk minus bk times ak is 0, but for all ak's. But since this is true for all contravariant vectors, we can make this, we can promote this to this kind of an equation. BI prime partial x prime I partial xk minus bk is just 0. It has to be identically 0. If this is true for all A's, then we've got to have this to be true. But once we've got that, we can just multiply both sides of the equation by multiply them this way. BI prime partial x prime I partial xk partial xk partial x prime L, say, and I can set this equal to bk. Okay, so this makes it a little easier. Is then equal to bk partial xk partial x prime L. On the other hand, this thing is just a chain rule. This thing is just delta IL. So this is B prime I delta IL. So this is B prime L. So what does that say? That says that B is a covariant vector. So that's an example of the quotient theorem. Now, the way I stated the quotient theorem was much more general, because I said this is true for arbitrary quantities. You could have all kinds of crazy indices on this, multiplied by a given kind of tensor, and if that is the suitable kind of tensor, then B is itself a tensor of a certain kind. And the proof of the general case is very much similar to the proof of the special case, so I'm not going to go any further with Okay, we've sort of run out of, well, we've completely run out of space unless I'm going to start erasing things, which I guess I could. But this is a good time probably to just introduce an idea here. So we have points P with coordinates x, and if we change coordinates, then P remains the same, but we might have a different coordinate system there. Now, suppose this is the point P on some manifold here, and suppose we change the coordinates a little bit. Then P is going to change a little bit. And the way it's going to change is going to be proportional to the change in the coordinates. And this extra thing here, this is obviously contravariant, this will be covariant, and this will be the invariant change in these physical points due to a change in these coordinates. Okay. These vectors EI, in general, are in some space, and I find it convenient, or at least, let us say, I find it natural to think of these vectors as being vectors in a larger space, and I'll illustrate that in a moment. But anyway, the dot product of these vectors is what we call the space-time metric, or the metric for the space. It needn't be space-time, it could be the surface of some geometric quantity. Okay, so that's the idea. Let me quickly go to an example. Suppose we have a sphere. So then we're looking at the surface of the sphere, and what might we have? Well, we might have coordinates here, theta, and then phi. And we would have points on the surface. Well, suppose we think of these points as points on the surface of a sphere in 3 dimensions. Okay. So then, these vectors, we would have E theta would be the partial derivative of the point with respect to theta. So that's E theta. I don't know how well that looks like. E theta is partial P with respect to theta. E phi is partial of this point with respect to phi. And then if you can take dot products of E theta with E theta, E phi with E phi, and in fact, E theta with E phi would typically just be 0. Well, we're sort of out of time. We'll get into this next time. But basically, there are various theorems due to Whitney and other people which say that if you have any kind of a smooth surface, you can imagine it that it's embedded in some higher dimensional flat space that's Euclidean or Minkowskian or whatever. And that means that all of these things in general relativity have a more concrete and visualizable form. In other words, it's just they're kind of a higher dimensional version of just the surface of a sphere. On the other hand, one of the triumphs of mathematics in the last, I guess in the 19th century or early 20th century, was the realization that you don't have to embed things. You can do everything on the surface. So those are two different points of view, and you can use both. All right, I guess, is there any questions? Yeah.
The UNM, in my modest,
What?
in just my very basic reading, I'm taking UNM 1 right now. A is usually just the vector potential, but you said that it also had the scalar potential.
Right, right. I explained the notation in the section on electrodynamics, which is on the whole chapter is on the class webpage. And the idea is that in ordinary E&M you use phi or V for the zero component, or A0.
For the scalar.
Yeah.
Okay.
And then there's an issue of signs because with special relativity, what we've got.
So this is it's a vector potential with 4 entries.
Yeah, it's the nifty way to think about it is that it's a one form like that. And A0 is the scalar potential to within a sign and a factor of C. And the other three A's are the thing whose curl gives you the magnetic field B.
Okay.
All right, I guess we can turn it off. Yeah, oh wait, there's one more question.
Well, my question is more, were you planning on covering anything on affine connections? Or was that outside of what you're going to do in general?
It'll be there in one form or another. Nope.